All right, so let's do some practice examples for 9.3, continuity. Okay, so for this first question, we have to graph the number line and express in interval notation. So we want the set of all numbers between -4 and 5, and we want to include both 4 and 5. So this means that I want -4, -3, -2, and so on to 4 and +5 inclusive. So let's look at the graphs that we have here. So A has that range that I wrote down, but notice how this is a bracket, which means we include that number, and this one's a parentheses, which means we don't include that number. So A is not the answer here. But looking at B, we see that we have a bracket on the 4 and a bracket, or -4, and a bracket on the 5, which means we want to include both. So B is our answer. Okay, and we can see that C isn't the answer either because there's a parentheses on -4. So that means the range would be all the numbers from -4 to 5, but not including -4. And then for D, there's the parentheses on both endpoints. So that's why B is the answer. Now, if we wanted to convert this to an interval notation, we can read it right from the line graph that we just made. So we have -4 and 5 as our endpoints, and then based on our line graph, we use brackets. All right, so A is our answer. Let's try another one. So this one, we want the set of all real numbers between -2 and 1. We want to include -2, but we don't want 1. So that means I want -2, -1, 0, 1.9, I'm sorry, 0.9. But we don't want 1. So if we look at our options, the parentheses on -2 means that we're not including 2, so we can already exclude A and C for that matter. So B and D have the brackets, which is good because that's what we want for -2. And now we have to decide, do we want a bracket for 1 or do we want a parentheses? Because we're excluding, we denote that with a parentheses, so D is our answer. And then again, we can just convert it to interval notation real quick. Let's do our endpoints. And then the bracket means include -2, and a parentheses means exclude 1. And so our answer is A. Okay, so different kind of question. We want to sketch a possible graph of f of x where f of 1 is equal to 3, and the limit as x approaches 1 is also 3. Okay, so let's do the first condition. Let's go through the graphs and see which one has f of 1 equals 3. So this is 1. So if I go up to this point, right, I want to go to the filled in point, and that is 3. So the first condition is good here. How about B? So here, f of 1, we have to look at this point. So f of 1 here is 1. So B is not one of the answers. How about C? We have 1 here, and that's 3. So f of 1 does equal 3 here. So C works out. And then let's check D. And so it's not filled in, so f of 1 does not exist. Okay, so D's not good. All right, so now we're going between A and C. And so let's look at our second condition. We want the limit as x approaches 1 of f of x goes to 3. So let's look at the limit here. So at 1, I see if I'm coming from the left-hand side, okay, I'm approaching 3. So the limit as x approaches 1 from the left-hand side of f of x is 3. However, if I'm going from the right-hand side, what value am I approaching? It appears to be 1. So because they're not equal, I can't say that the limit as x goes to 1 of f of x is 3. It does not exist here. So let's throw out A, and C is likely our answer, but we can verify. So again, you want to do the same game where when you're finding the left side limit as we approach 1. And so if we go from the left, trace left to right, it looks like we're going to 3. And then let's check out the right side limit. Start from the right and go towards 1. And it looks like we're approaching 3. So that's why our overall limit, because they're equal, is also 3. So C is our answer here. And then is f of x continuous at x equals 1? So by definition, whenever we have f of 1 equal to 3, and that's equal to the limit as you approach 1, which we have, all right, by definition, we have continuity. And we might see in the next problem where this may not be the case. So let's take a look. So here we're looking at a graph that has f of 3 is equal to -1, and then the limit as x goes to 3 is 1. So notice how they're not equal. So just think about what that means in terms of continuity for a second, but let's find the graph. So let's do my first condition, f of 3 equals -1. So 1, 2, 3. So my f of 3 here is +1, so not any good. Let's go here, f of 3 here. My f of 3, notice how there's no filled in points along where 3 is, so f of 3 does not exist here. Okay, so we can throw that one out. And 3, it does appear f of 3 here is -1, so that's good. And then let's just check D. So we have 3, and again, f of 3 here is 1, so we could probably throw out D. And let's just verify that C has the limit as x goes to 3 of f of x. And how we do that is let's look to the left. So let's travel left to right towards x equals 3. And it looks like we're going to 1. And let's do the opposite. If we do the limit as x approaches 3 from the right of f of x, let's go from right to left towards 3. And we're also approaching 1. So notice how even though my function is -1 at x equals 3, my limit still can exist at a different value. And this is because this is a point discontinuity. And so kind of just hinted at this, but the function is not continuous at x equals 3, right? Because if I wanted to graph this, I would have to pick up my pencil, right, to put in this point. So that's another way that you can determine continuity, at least graphically. And so the reason why is, let's see, so it's discontinuous at x equals 3 since the limit does not exist. Well, the limit does exist, right? And it's 1 because these two are equal. So the overall limit is 1. So A is not correct. It's discontinuous at x equals 3 because f of 3 does not exist. Well, that's not true because we have this point. So B is also not correct. So C is our answer, and that's because our limit does not exist or is not equal to our function value, right? Because we were given that it was -1, our function value is -1, but the limiting value is 1. So that's why C is the answer here. Okay, so now new type of question. We're using this graph on the right hand side to estimate this value, f of 1.9. So all we're going to do is we're going to find where 1.9 is. So here's 1 and 2. So 1.9 is about here, give or take. And this is an approximation, so you don't have to worry about getting the exact number. So all I'm going to do is I'm going to look up or down because my function corresponds to this piece when I look up, because if I look down, my function doesn't exist. So I would say the answer, so then I draw it over to this f of x. This is 1, 2. So I might call it maybe 2.1. It might even accept 2, but as long as you're close. Yeah. Okay, so let's do another one. So we want to know what the function value is at x equals negative 1.1. So again, let's try to find that value. So here is 1, negative 1, and here's negative 2. So negative 1.1 lives about here. So it's negative 1.1, okay? So let's just look up or down until we hit the function. So in this case, we're going to look up. And so the point's about here, and I would call that 1. Okay. Okay, so now we have this function, f of x, 7x minus 7, and we want to know if it's continuous and where. Okay, so 7x minus 7, that kind of looks like the equation of a line, right? Where we have mx plus b, where b is my intercept, my y-intercept, and m is my slope. So we could graph this if you want to. So my intercept, let me actually move it here. So my intercept would be negative 7, so that's where the point lies on the y-axis. Negative 4, 5, 6, 7. And then my slope tells me rise over run. So I'm going to rise 7 units and run 1. Rise over run. So 1, 2, 3, 4, 5, 6, 7, and then over 1. So now I have 2 points. I know it's a line, so I'm going to just connect it. More or less. All right, so it's the function of a line, so it's always continuous, right? I can always put in any number and get a number out. And so that's why it's negative infinity to positive infinity, which means just any number I can throw in there. It's also a form of a polynomial, so polynomials are always continuous by definition. Okay, so here we have a rational function. So a rational function just means that we have something in the numerator and then something in the denominator. Kind of looks like a fraction. Okay, so when we see rational functions, we have to be a little cautious because what do we know about fractions? We can't divide by 0, right? I can't do 4 divided by 0, negative 10 divided by 0, not good. And so what this problem creates are potential places for discontinuity. So always be cautious when you see a rational function to be thinking about that divide by 0 problem and try to find those points where we can encounter that problem. So m of x, so to find those points, all we're going to do is just solve for where the denominator is equal to 0. So the denominator is equal to 0 when x equals 3 and when x equals 5. So this means I can't put 3 or 5 into this function. So if I do m of 3, I get 3 plus 3 over 3 minus 3, 3 minus 5, which will give me 6, 0 times negative 2, which is 6 over 0, which is not good. So that's why we cannot put 3 into m of x, and for the same reason, we can't put in 5, right? Because that would make the denominator also go to 0. This will go to 0, and so the whole thing will again go to 6 over 0. Okay, so if you're a graphical learner, we can graph this as well and see that this is the case. Okay, so if we add, so 2, 3. So we might get to this later in the section, or maybe the next section, but basically these form asymptotes because I cannot put my function anywhere on these lines because that would indicate that I was able to put 3 or 5 into the function and get a number out. So these are like boundary lines where my function won't cross or it won't exist on these asymptotes. Okay, so, and if you graph the function, it would look something like this, where you would see I'm picking up my pencil to draw these individual sections. So we do have discontinuity. And so we would just make the interval from -infinity to +infinity, but we have to remove those points in between 3 and 5. So -infinity to 3, and then we want to include everything in 3 to 5, right? Because that's this piece. So 3 to 5, and then we want, this is 5 here. So now we're going to do this piece. And so that will be 5 to infinity. And this symbol here just means union, which just means or. So x could be this range, or this range, or this range, but not 3 and 5. Okay. Okay, so we want to use the sign chart to solve this inequality. We're going to use inequality notation and then interval notation. So for this problem, we want to find these partitions, which partitions would be where f of x is discontinuous, continuous, or f of x equals 0. And here our f of x is this polynomial on the left-hand side. Okay, so it's a polynomial, so it's always going to be continuous, right? I can always put in any number and get a number out. So we want to think about where can my function be equal to 0. And so let's factor, right? We want to solve for x. And so if we factor it, we get x minus 7, x plus 4. Okay, and then remember we're solving for 0, so my solutions would be x equals 7, x equals -4, and then these would be our partitions. So now let's use a number line to create a sign chart. So I want my numbers -4 on the graph and 7, so -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. I'm gonna extend this a little bit. You'll see why in a second. I'm gonna put just one more on the other side of our partitions because we'll need them. Okay, so I'm going to put these partition points. They're going to be open here because our inequality is less than. If it was less than or equal to, then I can fill them in, but we don't have the equal to case here, so that's why they're open circles. Okay, so next we want to find the signs for this interval, this interval and this interval. So notice how my two partitions basically chopped up my line into 3 segments, and I want to know what the sign is for each segment. So to do that, we want to test points. So let's test a number in this segment, in our first segment. So that's why I put the -5 there. All right, let's also test a number in this segment. I'm gonna do 0 just because it'll be easy. And then again, to test this last segment, I'm gonna test x equals 8. And so basically what I'm gonna do is I'm gonna plug in these numbers, and you can get the actual number, but I'm probably just gonna do a sign analysis, and then that will determine what sign each interval is. So if I'm gonna use the factored form just because it's a little easier, but you can use, this is the factor form, but you can use the original function as well. You should get the same answer. But anyway, if I plug in -5 for x, so using just signs now, so -5 -7, so that will give me a negative. So I'm just gonna denote it as a negative, and then -5 plus 4 will also give me a negative, right? -1. And so a negative times negative will give me a positive. So that's why this interval is going to be a positive, which I'll just write with a bunch of pluses. So let's play the same game for x equals 0. So I have 0 minus 7, 0 plus 4. So 0 minus 7 is going to give me a negative, 0 plus 4 is going to give me a positive, and a negative minus a positive will be a negative. And so this big interval in the middle is going to be minus, minus, minus. It's going to be negative, okay? And then for my last point, 8 minus 7, 8 plus 4. 8 minus 7 is going to give me positive. 8 plus 4 is going to give me a positive. So a positive times a positive is a positive. And so my last interval is a positive number. And so now let's return to the original question. We want to know, where is this less than 0? And when something is less than 0, that translates to when it is negative. Okay, when something is greater than 0, then that means when it's positive. So all I need to know is which interval is negative, right? Which interval is negative? And so we determined using our sign chart that this middle interval, right, is negative. And so all we have to do is just convert that back to inequality form. So that means I want any x value in between -4 and 7. And then it's between, but it's not equal, right? I'm not going to put less than and equal to and then less than and equal to, right? So that's why I don't have the equals here. So that's our inequality. And then to translate it to interval, we do the same thing, but now we don't have x, so we write the endpoints. And then remember a few questions back, we don't want to include -4 and 7, so we use parentheses for that. All right, let's try one more. So here we have the form x squared plus 12 is greater than x or 8x. All right, so let's get it back into that form where I have x squared plus, or let me get it back into the form where it's something is greater than 0. So to do that, I'm going to move the 8x to the other side, and to do that, I'm going to subtract it from both sides to get 8x squared minus, or x squared minus 8x squared plus 12. And so again, let's find those partitions. Here it's a polynomial again, so we want to know where my partitions, where f of x is equal to 0. So x, if we factor it, so -2 minus 6, right? And we want to know where they're equal to 0. And so our partitions are x equals 2 and 6. So let's draw our number line again. So I'm going to start at 1, 2, 3, 4, 5, 6, 7. Put 0 on here too. All right, and so let's put our partitions on. Are they going to be open circle or closed? Well, that depends on this inequality, and there's no equal underneath it, so they're going to be open circles. And so now remember, I want to know what the signs are for these intervals. We now have 3 intervals like the last problem. So let's pick some test points. So I'm going to test 0 for the first interval. I can do x equals 3 for the middle interval, and let's do x equals 7 for the last interval. So plugging in, I get 0 minus 2, 0 minus 6, which will give me a minus times a minus, which will eventually give me a positive. So plus, 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 and then if we put in 3 minus 2, 3 minus 6, I get a positive times a negative, which will give me a negative. And then 7 will yield a positive, right, because that's positive 5, so times another positive. And so I get positive. Oh, I forgot to write this. Minus, minus, minus. And then the last one is plus, plus, plus. All right, so I'm going to return to this form where I have it here that everything to the left is greater than 0. So unlike the last problem, now we're worried about greater than 0, which means positive. So which interval is positive? Okay, and so I see my intervals now are the first and last one. So this means I want everything to the left of 2 and everything to the right of 6. And so how we write that with inequalities is I want my x to be less than 2 and my x or my x can be greater than 6. And so let's see, 6C is our answer. So we have 2 and 6 here. Okay, and then for interval notation, I want everything to the left of 2. So this is the left interval, or I want anything greater than 6. So 6, this includes like 7, 100, and so on. All right, so here's our interval notation for this second part. Okay, so here we have a few statements, and we want to know which one is true. Okay, so a polynomial function is continuous for all real numbers. We know this by definition, but we can also rule out the other options. So it's most likely D, but let's look at A through C first. So this statement's false. A counterexample is f of x is this rational function. Well, that's not exactly a polynomial, right? It doesn't fit the form of ax n plus bx n minus 1 and so on, right? So that's why A isn't it. Square root again, not a polynomial, right? C, this is a polynomial, but that doesn't count as a counterexample because if we graph it, we know that's a parabola, right? It looks something like this. And that just means that it's always continuous. You can always put in any number and get a number out. So C is not it. So yeah, D is the answer just by definition. So now this statement saying if a function that is continuous at x equals 0 and x equals 2, then it has to be continuous at x equals 1, which I would hope you would recognize isn't true. But if not, let's look through the statements below. So the statement's false, a counterexample with a jump discontinuity at x equals 2, for example, this function. So this function, remember when I said look at rational functions, you want to think about that divide by 0? Well, we have the divide by 0 issue when x is equal to 2, right? Because if I plug in 2, I get 3 over 0. So we do have a discontinuity at 2, but we're concerned about discontinuity at x equals 1. So no to A. B, the statement's false. A counterexample is a function with a point discontinuity at x equals 1. For example, y equals 1 over x minus 1. And that looks pretty promising, right? Because, again, with the divide by 0 issue, that occurs at x equals 1. So this is a possible contender. C, the statement is true because if f is continuous at points A and B, then f is continuous on the interval of A to B. Not true, right? I feel like we've seen a few examples where, if let's say we have A to B, where it could be continuous at A to B, but somewhere in the middle, you can have an open circle, a filled-in point somewhere else. I mean, a ton of different options, right? You could have an asymptote where it goes like this, where you technically are continuous at A and B, but at somewhere in between, it's not. So C is also not good. And then let's look at D. Counterexamples with a jump discontinuity at x equals 0. Again, we're not concerned about x equals 0 here, so that's why B is our answer. Okay, so sketch a possible graph. So we have this kind of information where f of x is less than 0. Remember, this translates to negative. All right, and we also know where f of x is greater than 0, and so this would be positive. So let's see which graph corresponds to these conditions. So the first one says that from negative infinity to negative 2, I want my function to be negative. So negative infinity, I'm trying to make this bigger. Okay, so negative infinity starts all the way down here, right? And so negative 2, which is about here, we want that piece to be negative. So that works, right? It's below the x-axis. And then we also want it from 7 to infinity to be negative, which this is 7, and then out to infinity, x, right? We're going in the x direction, which means as my x gets really large, okay, so my y is below the x-axis. So this is probably the answer, but let's check on the other ones. Also, this graph is positive in between negative 2 and 7, right? It's above the x-axis here, right? So A looks like a pretty good option for this question, but let's look at the others. So for here in B, this seems to be negative 7 and 2, so it's kind of flipped. So that's your first indicator that this probably isn't the answer. So what it's saying is that f of x from negative infinity to 7, negative 7, right? So it is positive on the intervals of negative infinity to negative 7 and or from 2 to infinity, right? And then f of x is less than 0 or negative. It's below the x-axis, in between. So that does not exactly match what we were given. So let's throw b out. And we can also throw out d for the same reason, just because it's kind of the reverse of what they're saying, because we have two intervals where it's positive when they only want one interval, right? -2 to 7, so let's just throw out d as well while we're at it. But let's look at c and why c isn't the answer. Because it fits the form and number of intervals, but I imagine, let's see, so this is -7 and 2. So again, they switched those partitions, you can call them. So this function is negative. So it's negative when? From -infinity. Remember, we're talking about x, so -infinity to -7. And then also 2 to +infinity. And that's kind of the opposite of what we were given. And f of x is positive from -7 to 2. So they kind of just flip the endpoints. So that's why A is our answer. And then the x-intercepts of f, they are where the signs change, where the function crosses the x-axis, however you want to think about it. So if we use A, now that we know that's the right answer, our x-intercepts are where the function hits the x-axis, okay? So this is really where y is equal to 0. And so graphically, we found this to be -2 and this is 7. So our x-intercepts are -2, 7. All right, one more. So we now have the conditions that f is negative on -infinity to -infinity and 1 to 6, and f of x is positive on -4 to 1 and 6 to infinity. So let's go through each graph, and let's do the negative first. So negative, I want my graph to be negative from -infinity to -4. Remember, these pertain to the x values. So let's see, so my -infinity over here starts up here. And this is above the x-axis, so then this means that f of x is positive when my x is from -infinity to -4. So notice this is the opposite of what we want. So A is not the answer. And then similarly, that's why C is also not the answer, right? Because we start off positive when we want to be starting off negative as we're reading left to right. So between B and D, let's notice what the difference is. I think the intercepts, right? So this has an intercept, an x-intercept of -4. This one is 1, and this one is 1, 2, 3, 4, 5, 6, I believe. And then let's look at these intercepts. I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. -6 and -1, and then this one's 4. So notice the x-intercepts are different. So if we write out the intervals for where f of x is less than 0, what do we get? So my x intervals are from -infinity to -4, and where 1 to 6, right? We're 1 to 6. And then f of x is greater than 0 or positive when my x's are between -4 and 1. I'll write it this way. All right, so in between that interval and then from 6 to infinity. So that matches what we were given, right? So B is most likely our answer, but let's write them out for D just to make sure. So F is negative when my x is negative infinity to -6, and then between x equals -1 and 4. So, and then we also want to look when my f of x is positive. So we have this piece between x equals -6 and -1, and then 4 to infinity. So that looks like -6 to -1 and 4 to infinity. So notice how these two are different and how this one does not match what we were given. So that's why B is our answer. And then how we already used the x-intercepts in our analysis, but basically they're, again, where we cross the x-axis. So -4, -1, and 6. Okay, so these are our application problems for this section. So we have a first class postage is 45 cents for the first ounce and 15 cents for each additional ounce, up to a maximum weight of 3.5 ounces. So here, these are the numbers that we'll probably need to use, potentially this one. So they gave us these different, this is a piecewise function because we have different cases, right? So if I only have, well, it says, or any fractions, that just means any number between 0 to 1 for the first range. So between 0 and 1, the postage is just 45 cents for the first ounce or any fraction up to that. So that's why this one, I'm gonna write it over here so you can read it. It's 45. Okay, and so let's say I had my x is equal to 1.2, then we fall in this range, right? So what will happen is that I need to pay for the first this 0.45, right, for our first ounce, but then I need to pay 15 additional cents for the 0.2, which is my fraction, my additional. So I'm going to add 15 cents to this. And so this one will be 0.6. And then same for now, what if my fraction or my letter weighs 2.5? So now I'm talking about this range, right? So I'm going to pay what it was for the 2 ounces. So that would be this 60. But then I need to pay an additional 15 cents for the additional 0.5 ounce, right? So that's why I have to add 0.15. And so I get 0.75. And then finally, what happens if my package or my letter weighs 3.3? So now we're talking about this last case, right? Because 3.3 is between 3 and 3.5. So I need to pay for the 3 ounces, which we got from here. And then I need to pay 15 cents for the additional 0.3 ounce. So 1.5, 0.90. So my piecewise function looks like this. Just to write it a little more clear, if x is between 0 and 1 inclusive, so 60 cents if x is between 1 and 2 inclusive, 0.75 if my x is between 2 and 3, and 0.9 if x is between 3 and 3.5, because that's our maximum. Okay, so that's our answer. Now looking at B, we have these different graphs that maybe you haven't seen before, but they're called step functions because they kind of look like a staircase that you could kind of walk on. So what do we notice about P of X? Well, as my X gets larger, right, as we look down our piecewise function, my postage seems to increase, right? And that kind of makes sense. The heavier something weighs, the more I'm going to pay for it, right? So that's why as we look on our graphs, we want, as the X gets larger, we want our postage to go up. So almost like an upward trend like that, right? So A is a possible answer. B, you notice as X goes down, notice my package or my postage is going down. So we can kind of throw out B and C for that matter, right? Because it doesn't make sense that if something weighs more, then I'm going to pay less for it. So that's why B and C aren't the answers. So now we're stuck between A and D. And notice there's a very small detail between the two, is that the filled in points are at the beginning of the stair, or the step, right? But in D, it's at the end. So which one is it? So let's return to our P of X, our piecewise function, and notice that this corresponds to our X, right? So we want to know, where is the X being included? Is it being included in the front end or the back end of the step? And so if we look at our ranges, we notice that the equals is on the end of the range. And so D is our answer. Right, we can kind of verify that I should have my P of 1 should be filled in to 0.45, right? And so that's why we have this point here. Okay? So 2 more questions. So now we can use this graph now that we determined it's the right graph. Is P of X continuous at X equals 2.5? So let's locate 2.5 on the graph. That's right here. And so when we want continuity, we want the function to exist. So f of x exists a number. We can call it L, I suppose. And then we also want that to be equal to the limit. Let me write it this way, f of c. So you want the limit to exist and be equal to the value. So let's see, the f of 2.5, that, I think if we look back, if we look back, 2.5 will give us this case, right? So 0.75 cents. And then if we look up, that's right here. So this is probably 75.75. Okay, and then my limit as x approaches 2.5 from the left. So as I'm walking along from the left hand side, I'm approaching 0.75. So f of x is 0.75, and then let's look at what's happening to the right. So as I'm walking along, trace along right to left until you get to 2.5, and so we're still at 0.75. And so since all of these are equal, we have continuity. And that's what this last option's saying. Okay, so let's play the same game for the second part. Now we're concerned about x equals 3. So let's take a quick look at that. Okay, so now we have x equals 3, that's here. So if we look up, we see our f of 3 is equal to 0.75, kind of like before. All right, and then for continuity, I want to check, is my left-hand limit at 3 of f of x, is that equal to my right-hand limit? And then for continuity, is the overall limit equal to my function value at that point? So coming from the left, I notice that my function is approaching 0.75. But now let's look what happens when we approach from the right. It seems I'm approaching a different number, right? And I believe that was 0.9 that we found. So notice these two don't match. And so that means that our limit as x goes to 3, the overall limit, does not exist. That's because they're approaching two different numbers and we don't know which one it is, so we just say it does not exist. And so for continuity, we have to check if the overall limit is equal to the function value. It's not, so we can throw out the last example. And we can kind of see on the graph, right? I have to pick up my pencil to continue on to draw this graph. So you can always do a sanity check there. But let's see the reasons why. So no, because P of 3 does not exist. I'm sorry, I've been using F, but you can also just call it P. So P does exist, right? We found that it was this 0.75, so that's not the right answer. So no, because the limit as x goes to 3, P of x does not exist. Okay, so our answer here is no, because the limit as x goes to 3 does not exist. Okay, so moving on, our last application problem. So we have a table that shows the rates for natural gas charged by gas agencies during summer months. The customer charges a fixed monthly charge independent of the amount of gas used per month. Okay, so we have a base charge of $6, and then for the first 45 therms, we have 0.70, so suppose that's 70 cents, right? And then 50 cents if we're over that 45. So now we want piecewise function. We have a piecewise function where we're concerned about some x value between 0 and a threshold, and then x greater than that threshold. So we get our threshold from this table, right? We notice that the first 45 are this price, but then if it's over 45, then it's this price. So that's why we want this 45 here, is because we have these different conditions based on how many therms you have. Okay, so the base price is something that you get charged no matter how many therms, right? And then you need to add on your the amount per therm. So that's 0.70 times therm, which is x. Okay. So next, we have to do the second part of the piecewise. So what would that look like? So I think we did a similar problem, maybe 9.1, where we have a price for the first 35. So we have the base price, right? Base price. And then the first 45 therms. And then we want to add on additional, like over. What's your additional therms? So your base price is your $6, right? And your first 45 therms would be 0.70 x, right? But your x in this case is really 45. So I'm going to actually substitute in 45 for x, because I know that if my x is over 45, then I definitely have at least 45 therms. So I'm going to be paying at least this amount. And then the additional therms go for 0.5 times my x, which is my total therms. But remember, in this term, we already accounted for the first 45. So that's why I want to subtract out 45 therms. And so now we have our equation, which is 6 plus, and then I believe, what did I get for this? This is 31.5, this, and then this last one gives me 0.5x minus 22.5. And so if I fully simplify, I get 15 plus 0.50x. And so writing it as your piecewise function, I have 6 plus 0.70x if x is between 0 and 45, right, inclusive. And then my second piece is 15 plus 0.50x if x is greater than 45. All right, so now we want to graph f of, or s of x. Okay, so the graph, so we notice that these two pieces, they're basically lines, right? If we graphed them individually, we would get two lines. And so if we graphed them, you might get something that maybe this is the first line, and then the second line, it has a smaller slope. So that means that it's going to be less sloped. It's going to grow a little slower. So then our function, our s of x, would be kind of the combination of the two. So it would be something like this, which kind of matches what we see below, right? So that's how I'm getting, if I combine the two to make our piecewise. So if I look carefully at these, and it's kind of hard to tell on here, but on your end, you could probably hit this magnifying button if you need to zoom in a little, but it seems that this is growing at a steeper rate or a faster rate, and then this is a little slower, and that's what we want. So A is potentially correct. Now B, it looks like it's a little slower, and then it goes off steeper, right? And then same for C. C and B look similar. D and A look similar. So I'm just going to cross out B and C. You can also verify, what is this? So this is 50, 40, 30, 20, 10. So your y-intercept here is more likely to be 15 than 6, because 6 would be down here. So that's another reason why we would throw out B and C, is because the y-intercepts don't match, because my f of 0, or sorry, my s of 0, we would get that from this first piece. And so if I plug in 0 for x, I get 6. So that's another reason why B and C aren't it, because I have the point s of 0 is equal to 15 here. So now we're down to A and D. And notice the only difference are what the points are. Are they filled in or are they open? So quick indicator is looking at the first range. We can see that my 0 would be filled in, right? Because it says equals to. So A is probably the answer, but let's verify once more. So another way, so now we need to check, is this point filled in? So to get that point, I want to plug in, and I'm sure this corresponds to 45, because that's, again, what divides these two ranges, right? This 45. So I want to plug in 45 to both of my pieces of my piecewise function and see if they're equal. Because if they're equal, then they would meet at this point and it would be filled in. So is it equal to 15 plus 0.50 times 45? And if you do the math, I believe it comes out to be, let me see, 6 plus 0.7, so 0.7 times 45, so this is 6 plus 31.5, and this is 0.5 times 45, so this is 15 plus 22.5, so if we add them, we get 37.5 is equal to 37.5. So yes, they match, they're equal. And so that's why we want to fill this point in, because my F of 45, my S is equal to 37.5, regardless of which piece I used. And so that probably corresponds to 37.5, right? 0, 10, 20, 30. Okay, so A is our graph. Okay, so I think this is the last part. So is S of X continuous at 45? And we kind of hinted at it in the last question. So here's my 45, here's my 37.5, I believe. Yes. So remember, when we're talking about continuity, we need to know, is my F of, I can't get used to S of 45, is that equal to my limit as X approaches 45 of S of X? Are those two equal? And so how to get this, we need to look at the limit as X approaches 45 from the left of S of X, and the limit as X approaches 45 from the right of S of X. And so let's find those first. So if I'm approaching from the left, I'm going to trace left to right till I reach 45 on the X-axis. I look over to the Y and I see I have 37.5. Same game, but coming from the right. I notice I'm approaching that 37.5 again, so my overall limit is 37.5. And so what is my S of 45? So all we do is we look up or down. Here we're looking up till we hit it, over to the left, 37.5, so they are all equal. And so yes, it is continuous because of all those reasons that we just went through. Okay, I believe that's the end for this section. I hope you found this helpful, and stay tuned for 9.4.